So this video is still on the chapter, well, it's on the course of representation theory, and we are on the chapter of group representations. So I'm going to introduce a quick lemma here. Let phi be a representation from the group G to the general linear group over the vector space V. And this is a representation, so let phi be equivalent to a decomposable representation. So we have phi, and we know that phi is equivalent to, well, usually we write equivalent this way. We know that phi is equivalent to psi, and psi is a decomposable representation. So if this happens, then phi is decomposable too. Okay, this is an important lemma, and this video will be the proof for this lemma. Okay, I called psi here, right, the supposed other decomposable representation that is equivalent to phi. So let us skip this notation. So I'm going to call it psi. So psi will be a representation from G to GL. This is vector space V. Let us say W. Okay, it doesn't have to be the same vector space. And let us say that this psi, so psi is decomposable. Okay. Okay, psi is decomposable, and psi is equivalent to phi. Okay, so we have a linear transformation, or a transformation, from vector space V to vector space W. Okay, so of course this will be an isomorphism. Okay, for this to be an isomorphism, please check the previous videos. So, and since the representations are equivalent, we have the inverse psi j. Okay, okay, so we have W here. Let us pick W1 and W2 subspaces of this vector space. Let us say these two are non-zero invariant subspaces of W. Okay, but let us say that W is the direct sum of those two. Okay, you probably remember that we saw this in previous videos. We had V to V and V to W, so this is a transformation, right, to W. So this is a transformation, so W goes to W. So this is the representation, phi of G, and let us say this one is psi of G. Okay, so this is our old scheme. Okay, so this is true for this one. We could, if we left multiply T, we will have T of Fg, right? I'm left multiplying here. T of Fg equals, this will be the identity, psi of Gt, right? For all G in the group, of course. Okay, let us pick now V1, and let us say that V1 is, let us say that V1 is W1, so the one of the subspaces of W, and let us call V2 the W2 with the left multiplied by the inverse transformation. Okay. First, we claim that V will be equal to the direct sum of V2 plus V1 plus V2. So we got two subspaces for W, W1 and W2. Okay, and now we got two subspaces for V, V1 and V2. But we said that V is the direct sum of V1 and V2. But we called V1 the inverse transform of W1 and V2 the inverse transform of W2. Okay, if V is in the intersection of V1, V2, if this happens, then the transform of V will be in the intersection of W1, W2, two subspaces, right? But the transform, the intersection of W1, W2 can only be the set with the zero element. That's the only element that can be in the intersection of the two subspaces. So the transform of this object, so this image, has to be 0. Okay. But do not forget that T is injective, right? And since T is injective, so V has to be 0. This small v here has to be 0. This V in the big V. Okay. Now, if V is in the intersection of V1, V2, if the small v is in the vector space, then we have the transform of V will be W1 plus W2, right? For W1 in the big W1 and W2 in the subspace W2. What we have here is the transform of V, right? That I say it will be adding two W's, one from 1 and two from 2. Because that small v will be here in V, so its image will be here in W. Okay, but we are saying that W is a direct sum of W1 plus W2. But our V that is in the subspace V, in the vector space V, we said that V1 is this inverse transform of W1 and V2 is the inverse transform of W2. So V will be adding, and V is the direct sum of this. We assume that. So V will be the inverse transform of W1 plus the inverse transform of W2, and that will be in this V1 plus V2. And since this happens, so we conclude that yes, V has to be the direct sum of V1 and V2. But now that we proved that V is the direct sum of V2 and V2, V1 and V2, we still have a question. V1 and V2, are they G invariant? Well, if V is in the any of the vector spaces v1 or v2 or whatever, then phi g of v, small v, will be according to T transform psi g tv, because they are equivalent, right? But the transformation of v is an image, so it should be in the space wy, right? So this implies that psi g of tv, of the image, has to be and one of the w's, w1 or w2, in one of the subspaces, because wy is g invariant. So phi g of v will be T inverse psi g t, that is in the inverse of wi. But what is the inverse of wi? That's one of the subspaces of v, and this concludes the proof. So if phi, an equivalent representation, if phi, a representation, is equivalent to a decomposable representation, in this case psi, then phi will be decomposable. The proof is not easy, but if you reread it, you will see that it's not very hard. In a certain way, what we do is we get psi, and we use this fact here, that the transformation of phi of g, so this is equal to psi g transformation, or we use this one, right? Because this is the one that we know that it is decomposable. So we want to prove that phi of g is also decomposable, okay? So just use this t from the objects to the images, okay? And since this one is decomposable, okay, we get w, for instance, and we decompose it because w is decomposable, okay? And it's easy to prove that then v is decomposable. So phi has to be equivalent to this decomposable. Phi is equivalent by hypothesis. No, what I mean is since psi is decomposable, you prove that phi is decomposable too.